Hi there, Mr. Sutton here, bringing you the AB Calculus 4-8 homework solutions on mean value theorem. For this problem, g is some twice differentiable increasing function of t, and we have 0, 20 and 10, 220 as 2 points that are on this function. Based off of that, what's true on the interval from 0 to 10? And here are our options. So we're talking about g prime and g double prime. Since we're given two values at the endpoints of the interval, and we're talking about the instantaneous rate of change somewhere on the interval, it would be a good idea to find the average rate of change, because the mean value theorem might help us here if we can find an AROC that matches an IROC in one of these answer choices. So finding AROC here, we've got 220 over 20 and 10 over 0 in our fraction. So that's 200 over 10, or exactly 20. All right, so that's our average rate of change. Let's now look at our different answer choices. So choice 1, g prime equals 0 at some t in the interval. Well, we're not really guaranteed that that has to be the case. Our function starts at 20 and goes to 220, so it looks like at some point it's going up. We're not guaranteed that it equals exactly 0 for the slope unless we had an AROC of 0. But we have an AROC of 20. Since 0 does not equal 20, we can't guarantee that we have a 0 instantaneous rate of change anywhere on there. Next one, g prime equals 20 for some t in the interval. Well, that's exactly what we have here. The MVT says since you have a continuous differentiable function, then IROC equals AROC at some t value on your interval from 0 to 10. So choice B looks like the right answer based on the mean value theorem. But let's look at C and D. You should always read all the answer choices. So for C, we're saying the second derivative is 0, and for D, the second derivative is positive everywhere on the interval. C is basically saying we're guaranteed to have no concavity, like a straight line, from 0 to 10. And D is saying that we're concave up across the interval, so doing this kind of thing like an exponential function. But we could be increasing and concave down the whole time. We could be doing one of these deals. Kind of like a logarithmic function. So we can eliminate C and D for that reason, and choice B then is the only one that makes sense. For this problem, we're given the graph of a differentiable function f on a closed interval from -4 to 3, and we want to know how many values of x in the open interval satisfy the conclusion of the mean value theorem for our function on this interval. So mean value theorem basically says AROC equals IROC for some x value on an interval if you have a function that is continuous and differentiable. They told us this was differentiable, so we get continuity for free, and we just have to find the places where the instantaneous rate of change equals the average rate of change across the whole interval. So our next step on this problem, we're going to find the average rate of change. That's going to be the y value -3 minus the approximate y value over here of 1, all over 3 minus -4 for the x values. So that comes out to -4/7 for our average rate of change. So I'm going to now make a little table with all my x values and the approximate instantaneous rate of change at those. And we'll just see, based off of this, how many times we have to pass through -4/7 for a slope. So at -4, I don't know what that slope is. We're just going to call it positive. At -3, that looks to be a slope of about 0. At -2, looks like about -1 for the slope. Same thing down at -1 here. Over at 0, this is a slope of approximately 1/2. Over at 1, our slope kind of tapers off to 0. At 2, I'll call that -1/2. And 3, that's just negative. I'll call it -2, but it's very negative. It's more than -1. So how many places do we have to pass through -4/7 here? Now, we're guaranteed that we're going to hit all the slope values in between these various numbers because we have a differentiable function. So I can't get -4/7 going from positive to 0. I can get it, though, between 0 and -1. And also somewhere between this -1 and this 0, maybe somewhere in this area. And once again between 0 and -2, maybe somewhere around here. So that's 3 different times I have to go through the slope of -4/7. Now, another way you could do this is just get a straight edge from here to here and then just eyeball it how many places you have that same slope instantaneously for a tangent line on here. Either way, you'll come up with 3, which is going to give us answer choice D. either by eyeballing or doing it the table way. For number 3, we want to figure out where this function f on the closed interval from 1 to 3 has an instantaneous rate of change equal to its average rate of change on that interval. So we're basically asking, where does a rock equal I rock? A rock on this, that's going to be f of 3 minus f of 1 over 3 minus 1, and we want to figure out where that equals f prime. Well, f of 3, that's 27 plus 15, so 42. F of 1, that's 1 plus 5, so 6. So we've got 42 minus 6 over 2, and we want to know where that equals f prime, which is going to be 3x squared plus 5. Okay, well, that's going to be 36 over 2, which is 18, and we can subtract this 5 to get us 13 on the left side. Dividing by 3, we've got 13 over 3, and then we'll square root that. And I would write plus or minus here, square root of 13 over 3, except that if you look at the answer choices, none of them are negative, so we don't need to worry about that here. But looking at the answer choices, it looks like choice B is a match, so there we go. For number 4, we have a function g that is continuous on a closed interval 1 to 4. G of 1 is 5, and we also have the point 4, 8 of the following conditions, which would guarantee that there's a number c on the open interval from 1 to 4, where g prime of c equals 1. Well, if we're trying to guarantee that the instantaneous slope equals a certain value, that sounds a lot like the mean value theorem. Mean value theorem talks about the instantaneous rate of change equaling the average rate of change on an interval. So let's calculate the average rate of change given the beginning and the ending points of this interval. So for a rock on this, we've got 8 minus 5 over 4 minus 1. That comes out to 3 over 3, which is 1. So we do have an average rate of change of 1. The MVT guarantees that this average rate of change will equal an instant rate of change somewhere on the interval if the function is differentiable on the interval in question. So let's look at the answer choices, because that's the only thing they didn't give us here was differentiability. They gave us continuity, but not differentiability. Looking at our answer choices, we have increasing, that has nothing to do with MVT. Differentiable, that's what we're looking for, but let's just consider the others. G has a maximum value, we don't really care about that. The graph has at least one horizontal tangent, we don't need that either. Differentiability it is, choice B. For number 5, if f of x is sine of x over 2, there exists a c in the interval pi over 2 to 3 pi over 2 that satisfies the mean value theorem. Which of the following could be c? So for this one, we're basically trying to figure out a c such that f prime of c, if you find the derivative of this and plug in that number, equals the average rate of change from pi over 2 to 3 pi over 2. So we need to figure out the average slope on this interval of this function, and then figure out the f prime, that value that makes that happen. So average rate of change, we're going to have sine of 3 pi over 2 minus sine of pi over 2 all over 3 pi over 2 minus pi over 2. So this mess here. So let's take this term by term, and this was not a calculator question. So this is really sine of 3 pi over 4, which is sine of 135 degrees. That's radical 2 over 2. This is sine of pi over 4, which is 45 degrees, also radical 2 over 2. Down here, this is going to be pi if you reduce the 2 pi over 2 that you're going to get. So up top, we've really got 0, which means that regardless of what we have down here, this whole thing is 0. So we're trying to figure out where this derivative of this function here comes out to 0. What is the derivative of sine of x over 2? Well, that's going to be cosine of x over 2 times a tail of 1/2. Don't forget the chain rule. So we're setting this equal to 0 and solving for x. Well, multiplying both sides by 2, we just get cosine of x over 2 equals 0. Inverse cosine of 0, we're asking at what angle in radians does the x value equal 0. That happens at the top and the bottom of the unit circle. So at pi over 2 and 3 pi over 2. But we can't stop there. We haven't quite isolated x yet. We have to multiply everything by 2 now. So that means that x could equal pi or 3 pi. And I could have kept going, but we have a very limited range that the x's are going to be in, so I'm just going to take the 2 on the classical, spin around the unit circle, and work with those. So x could be pi, x could be 3 pi, it could be 5 pi and 7 pi. We could keep going. Only pi, though, is between pi over 2 and 3 pi over 2, and that means choice D is the answer we're going to pick. For number 6, we've got a function that's continuous and differentiable on the interval from -2 to 1. And we know that f of -2 is -5, f of 1 is 4. Based off of all this, which of these statements could possibly be false? So the key on this one is realizing that with the continuity and the differentiability, we've actually got the conditions for all 3 of our big value theorems. The IVT, EVT, and the MVT all apply on a continuous and differentiable function on an interval. So let's look at these answer choices now in light of this. First one, there's a c between -2 and 1 such that f of c equals 0. Basically, they're saying we're guaranteed to get a y value of 0 somewhere on the interval. Well, looking at our starting y value, we're starting at -5, we're ending at +4. The intermediate value theorem, IVT, guarantees that we're bound to hit 0 as a y value somewhere between those y values. So this first statement can't be false. It has to be true by the IVT. Next statement, there exists a c value such that f prime of c equals 0. So they're saying we're guaranteed to get an IROC, a slope of 0 somewhere on this interval. Well, the MVT says that if you have a continuous and differentiable function, you're guaranteed to hit an IROC value that matches your AROC, your average rate of change value. So let's figure out the average rate of change from this to this point here. So we've got 4 minus -5 over 1 minus -2. That's going to be 9 over 3, which is an AROC of 3. So we're guaranteed to hit an instantaneous rate of change of 3, but not 0. So this could possibly be false. But let's take a look at the other answer choices just to confirm. So for the next one, they're saying we have an f of c that equals 3, a y value of 3. Well, 3 is between -5 and 4. So again, by the IVT, we're guaranteed to hit 3. Next one, we've got f prime of c equaling 3. Well, now they're saying we have an instantaneous rate of change of 3. We are guaranteed to hit one of those because the average rate of change is 3. So by the MVT, we can rule out that answer choice. The last one, there exists a c value such that when you plug it in, it is bigger than or equal to all the other y values on the whole interval. They're basically saying there's guaranteed to be a max value somewhere on this closed interval. Well, that's the EVT, which is absolutely true, again, if you have a closed and continuous function on an interval. So by the EVT, we can rule out choice E. That leaves us with choice B. For number 7, f is a continuous function on the closed interval a to b. Which of the following must be true? So choice A, there's a number in the open interval such that f of c equals 0. This isn't necessarily true. There are lots of continuous functions we could draw that don't go through the x-axis and have y values of 0. So let's take a look at the rest of these answer choices. There's a number c in the open interval such that f of a less than f of c less than f of b. Now, this one looks a little bit more attractive. It kind of looks like the intermediate value theorem, but it definitely doesn't account for everything. For example, what if our continuous function is a horizontal line? Then the starting y value couldn't be less than the ending y value. And for that matter, how do we even know that f of a is less than f of b? I mean, how do we know we're not starting high and ending low? So this kind of breaks down if you take a closer look at it. Taking a look at c, there's a number such that f of c greater than or equal to f of x for all x in a to b. This is basically saying we're guaranteed to have an absolute max on this interval, and that has to be true because this is continuous on a closed interval. That's the extreme value theorem in action, guarantees a max and a min. So C is probably going to be the answer here, but let's just make sure we can really rule out these other ones. D, there's a number in the open interval such that f prime of c equals 0. Well, no, we're not guaranteed that this continuous function ever has a slope of 0. For example, what if we have the line y equals x? That's continuous, but always has a slope of 1. And for this last one, there's a number in the open interval such that f prime of c equals all this stuff, basically saying that the instantaneous rate of change equals the average rate of change on the interval. And this would be true by the mean value theorem if they had told us that this function was also differentiable. They didn't say it was differentiable, just continuous. So because we could have things like cusps and vertical tangents and other weird things in here on a continuous function, we can rule out E as well. So it's really just choice C then that we can pick. For number 8, we're given a continuous and differentiable function on the closed interval 3 to 7, and the table above gives us some selected values of f on the interval. Based off of what we see here, which of these has to be true? So statement 1, minimum value of f on 3 to 7 is 12. Well, that is certainly the smallest value we see in the table. However, how do we know that there isn't a smaller value on one of the non-integer function values? How do we know that, for example, f of 4.5 isn't even less than 12? So we can't say number 1 for sure. Number 2, there exists a c somewhere such that f prime of c equals 0. Well, if we have one of these intervals and we're trying to make statements about the instantaneous rate of change somewhere on the interval, the mean value theorem is a good place to check. Remember, mean value theorem says a rock equals I rock somewhere on the interval if you have a continuous and differentiable function. So let's see if we can figure out the average rate of change for the whole interval here. So we've got 20 minus 20 over 7 minus 3. That comes out to 0 over 4, so 0 overall. Since we have continuous and differentiable function and an average rate of change of 0, we're guaranteed that there's an I rock that equals that, namely 0, somewhere on this interval. So statement 2 is true. Now statement 3, f prime of x is greater than 0 between 5 and 7. Well, from 5 to 7, we're definitely increasing from 12 to 20 on the y values. So we can definitely say that there is, at some point here, an average rate of change that is positive, or else how could you go up? However, we cannot say that for this entire interval, the function is increasing. There might be somewhere in between these integer values where the function is going up and down. So because we could be changing directions for the parts of the table that we don't see, we can't say number 3 for sure either. So then it's just statement 2, choice B, that we can say for sure. For number 9, we have this polynomial function. Application of the mean value theorem on the interval 1 to 3 guarantees the existence of a c value between 1 and 3 such that f prime of c equals. So mean value theorem says that if you have a continuous and differentiable function, which we do here because this is a polynomial, we're guaranteed that the instantaneous rate of change somewhere on that interval equals the average rate of change, the a rock, for the whole interval. So our task then is we have to figure out the average rate of change, and then we're guaranteed the I rock equals that. So that's going to be f of 3 minus f of 1 over 3 minus 1. F of 3, we got to plug it in here, and this was a no calculator question, so be careful doing this. So that's going to be, let's see, 2 times 27, so 54, minus, this is 4 times 9, so 36. 54 minus 36 is 18, plus 1 is 19. So we have 19 for f of 3. For f of 1, that's going to be 2 minus 4, which is negative 2, plus 1, which is negative 1. So 19 minus negative 1 all over 2. So that's going to be 20 over 2, which we have to simplify because this is multiple choice here. Comes out to 10. So by the MVT, we're guaranteed there's an f prime of c that equals 10 somewhere here, choice C. For number 10, we've got this coffee dripping problem where the amount of coffee in a cup is given by a differentiable function whose selected values are shown in this table. Using the data in the table, we want to approximate c prime of 3.5, and they want us to show the computations and indicate units of measure. So we're asking for the instantaneous rate of change of ounces per minute of coffee at 3.5 minutes. Well, they didn't give us that in the table. They didn't even tell us the amount at 3.5, but that's okay. To approximate an instantaneous rate of change, we can use the average rate of change on an interval that contains 3.5. So if we find the A rock from 3 to 4, that should give us an answer that's close enough. So we'll do C of 4 minus C of 3 over 4 minus 3. That's 12.8 minus 11.2 over 1. And honestly, once you've plugged in numbers for C of 4 and C of 3, you can just put the units of measure and be done, and that's a complete answer. If you want to get fancy and simplify this, you do so at your own risk. It would be 1.6, and the units of measure is going to be ounces per minute. For number 10, part B, they want to know if there is a time between 2 and 4 where the IROC equals 2. Now, if you're trying to show there's an instantaneous rate of change of a certain value, the best way to do it usually is to use the mean value theorem and show that there's an average rate of change equal to the value you're trying to justify. So let's check out the AROC for this function on the interval from 2 to 4. So that would be C of 4 minus C of 2 all over 4 minus 2. That's 12.8 minus 8.8 over 2. And since this is not the final answer, since we're actually trying to show that this matches something else, we actually do have to take this out all the way without a calculator. So that would be 4 over 2, which is 2. So 2 ounces per minute, that's our average rate of change on the interval from 2 to 4. That matches the instantaneous rate of change we were trying to show existed. Before we can get credit, though, we do have to do a little bit more digging here. We're using the mean value theorem here, and that's only going to work if we have the condition of the mean value theorem, which is that you have a differentiable function. Now, looking up here in the original problem, they did say, they spelled it out, that we have a differentiable function. So one way you could actually write this up to get full credit, you could say, since C is differentiable, which they told us, so you don't have to prove it more than just mentioning it, but you do have to mention it, there's an x value on 2 to 4 where the IROC equals the AROC over the whole interval. You don't have to write mean value theorem to get credit, but it's nice if you do. So that's one way you could get credit on this one. For part D, we're given this function here which models the amount of coffee in the cup in ounces. Using the model, we want to find the rate at which the amount of coffee in the cup is changing at t equals 5. Well, if we want the rate that it's changing at, we just need to take the derivative of this, which we're going to have to do by hand because this is a no calculator question, and just plug 5 in for t. So when you're doing this, the 16 goes away. You're going to have negative 16e to the negative 0.4t times the tail of the inner function, negative 0.4. Now, you could actually multiply that by 16 and simplify it, which I did. You end up with 6.4 e to the negative 0.4t. You didn't actually have to simplify that to 6.4, though. You could have left it unmultiplied. But let's keep going. So now we have to plug in 5 for the time. And if you stick the units on the end, you could actually be done at this point in the problem. But I went and simplified that to negative 2 in the exponent. At some point, though, you do need to stick on the ounces per minute to get credit on this one.